What if everything you know about reality is wrong? What if the world around you, the very foundation of your existence, is just an illusion shaped by your perception? Can a particle exist in two places at once? Can two objects be so connected that they influence each other instantly, no matter how far apart they are? And what if the act of simply looking at something changes its very nature? Quantum mechanics doesn't just challenge our understanding of the universe, it flips it upside down. It defies logic, contradicts common sense, and raises questions that seem impossible to answer. Are we living in a world where reality is nothing more than probabilities, where certainty doesn't exist? Could it be that the universe is far stranger and scarier than we ever imagined? Or did they just come from anywhere? Well, let's find out. Quantum reality is very different from the everyday reality we experience. At the quantum level, where atoms and subatomic particles exist, the rules are nothing like the ones we observe in the larger familiar world. In classical physics, objects have specific properties like location, speed, and mass, and they follow predictable patterns. If you know an object's position and speed, you can calculate where it will be in the future. But in quantum mechanics, particles do not have definite properties until they are observed. Instead, they exist in a state called superposition, where they hold multiple possible properties at once. They only decide on one state when measured. This idea is completely unlike classical physics, where objects exist in a single, defined state at all times. Another strange phenomenon is quantum entanglement. When two particles become entangled, their states are connected, so that changing one particle instantaneously affects the other, no matter how far apart they are. This defies the classical idea that objects can only interact through direct cause and effect processes over a distance. Quantum mechanics also introduces the concept of uncertainty. According to Heisenberg's uncertainty principle, you cannot precisely know certain pairs of properties, like a particle's position and momentum, at the same time. This uncertainty contrasts sharply with the predictability of classical physics. These quantum behaviors can seem strange and counterintuitive because they challenge our natural understanding of how the world works. Scientists find it hard to connect these ideas with the stable, predictable reality we experience every day. This suggests that our everyday understanding of reality might only scratch the surface of a far more complex underlying structure. A key principle of quantum physics is wave-particle duality. Particles like electrons and photons can act both as waves and as particles, depending on how we observe them. This was famously demonstrated in the double-slit experiment, which showed that particles create wave-like interference patterns when unobserved, but behave like individual particles when observed. We see this duality in light. When light passes through a prism, it bends based on its wavelength, splitting into a rainbow of colors. This bending is a wave-like property. However, when light reaches your eyes, your receptors detect specific wavelengths as individual particles of energy called photons. Each photon carries a small packet of energy, called a quantum, and the energy depends on the wavelength of the light. Different receptors in your eyes absorb photons with different energy levels, which allows you to distinguish colors. This interplay of wave and particle behavior is central to quantum physics and highlights the unique nature of the quantum world. Superposition. In quantum mechanics, particles can exist in multiple states at the same time, a concept called superposition. For instance, an electron can be in several positions or energy levels at once. However, when we measure it, the particle chooses a single state, collapsing from its multiple possibilities. This means particles only show definite properties when observed. Entanglement. Quantum entanglement describes a unique connection between particles. When particles become entangled, the state of one instantly affects the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance because it challenges our usual ideas about cause and effect and how objects interact across space. Uncertainty principle. The uncertainty principle, introduced by Heisenberg, states that we cannot precisely know certain pairs of properties at the same time, like a particle's position and momentum. The more accurately we know one, the less accurately we can know the other. This uncertainty isn't due to faulty tools, but is a natural feature of quantum systems. Quantization of energy. In quantum mechanics, energy comes in tiny, indivisible packets called quanta. For example, electrons in an atom can only occupy specific energy levels and cannot exist between them. This explains phenomena like atomic spectra and helps us understand the structure of atoms and molecules. Quantum tunneling. Quantum tunneling allows particles to pass through barriers that, under classical physics, they should not be able to cross. This happens because particles behave like waves, with probabilities that can leak through barriers. Quantum tunneling is key to processes like radioactive decay and the functioning of certain transistors. The challenge of quantum mechanics. Quantum reality is hard to grasp because it contradicts the predictable and logical framework of classical physics. In classical physics, objects have fixed properties, follow clear cause and effect rules, and behave predictably. At the quantum level, however, particles behave unpredictably and introduce concepts that feel strange and counterintuitive. The uncertainty principle highlights the limits of what we can know. Unlike classical systems where precision is possible, quantum systems come with inherent uncertainty, making it impossible to simultaneously measure certain properties like position and momentum with full accuracy. This reveals a fundamental limit to knowledge at the quantum scale. The principle of superposition suggests that observation plays a direct role in shaping reality. Particles remain in multiple states until observed, and the act of measurement causes them to collapse into a single state. This challenges the idea of an independent universe and raises questions about whether observation and consciousness influence reality itself. Finally, entanglement reveals that particles can interact in ways that defy traditional notions of space and time. When entangled, two particles affect each other instantly, even if separated by vast distances. This phenomenon breaks classical ideas about how interactions should work, suggesting a reality that operates beyond the limits of space and causality. Together, these principles form the foundation of quantum mechanics, forcing us to rethink how the universe works while introducing ideas that continue to challenge even the most seasoned scientists. The concept of wave-particle duality shows that particles, like electrons and photons, can behave both as particles and as waves. This challenges the classical idea that objects must be one or the other. It forces scientists to rethink what particles are and makes it difficult to apply traditional models to explain the quantum world. Quantum mechanics works with probabilities rather than certainties. Instead of following clear, predictable paths, particles exist as a range of possibilities and only settle into specific outcomes when observed. This idea can feel unsettling because it suggests the universe may not be entirely predictable. For scientists who seek order and control, this probabilistic nature represents a significant shift in thinking. Over the years, scientists have developed different interpretations of quantum mechanics, such as the Copenhagen interpretation and the many worlds interpretation, to explain its strange behavior. However, none of these interpretations has been universally accepted, leaving many questions about the true nature of reality unanswered. These aspects of quantum mechanics challenge the core ideas of classical physics and introduce mysteries that are hard to reconcile with the goal of fully understanding the universe. This quantum weirdness not only questions what we know about reality, but also stretches the limits of what science can explain. Quantum mechanics is unsettling to scientists because it reveals mysteries that go against the predictable framework of classical physics. In classical physics, knowing the starting conditions of a system allows us to calculate its future with certainty. Quantum mechanics, however, shows that at its core, events are probabilistic. Particles follow probabilities rather than predictable paths, suggesting the universe may be less orderly and more chaotic than we previously believed. The uncertainty principle adds another layer of complexity. It states that we cannot know certain properties, like a particle's position and momentum, with complete precision at the same time. This is not due to limitations in our tools, but is a fundamental feature of quantum systems. For scientists, this means that some aspects of nature will always remain beyond our ability to measure or fully understand. The idea of superposition, where particles exist in multiple states until measured, also challenges the concept of an objective reality. If observation determines a particle's state, it suggests that reality may depend on perception, raising deep philosophical questions about whether we shape the world just by observing it. This blurs the line between science and philosophy, making some scientists uncomfortable with the idea that science might not be entirely objective. Quantum mechanics doesn't just challenge scientists intellectually, it also pushes them to confront philosophical and emotional uncertainties. It reveals a universe that is both fascinating and deeply perplexing, forcing us to reconsider our understanding of reality and accept that some questions may remain unanswered. Real-world examples like Schrödinger's cat and quantum entanglement vividly illustrate the strange and perplexing nature of quantum mechanics, often making reality seem unreal or profoundly unintuitive. These examples challenge the concrete, predictable worldview that many scientists hold, pushing the boundaries of what we believe to be possible. The famous thought experiment proposed by physicist Erwin Schrödinger highlights the strange concept of superposition in quantum mechanics. In this scenario, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer set to release the poison if the atom decays. The decay of the atom is a quantum event, meaning it can both happen and not happen until observed. According to quantum mechanics, until someone opens the box, the cat exists in a superposition of being both alive and dead. This paradox forces us to grapple with the idea that quantum particles, and, hypothetically, even larger systems like a cat, do not exist in a single definite state until they are observed. For scientists, the implication that reality doesn't settle into a defined outcome until it is observed challenges classical notions of existence. Schrödinger's cat raises unsettling questions about whether observation affects reality itself, making scientists reconsider the nature of objectivity and the role of the observer. Quantum entanglement, famously described by Albert Einstein as spooky action at a distance, is another mind-bending phenomenon. When two particles become entangled, their states become linked, so that measuring one particle instantly determines the state of the other, no matter how far apart they are, even if they're on opposite sides of the universe. This phenomenon seems to defy the classical idea that information cannot travel faster than the speed of light and challenges the notion of separable, localized objects. For scientists, entanglement is perplexing because it implies a form of connection that bypasses traditional ideas of space and time. Experiments confirming entanglement suggest that particles can influence one another in ways that seem impossible under classical laws, hinting at a level of interconnectedness in the universe that we do not fully understand. This phenomenon unsettles scientists because it challenges the boundaries of space, causality, and our understanding of how objects interact. It suggests that reality might be far less local and more interconnected than we can readily comprehend. These examples reveal a quantum world that operates on principles far removed from the concrete, predictable behavior of classical objects. For scientists used to working with clearly defined, observable phenomena, the unpredictable and observer-dependent nature of quantum mechanics makes reality itself seem more like an abstract, shape-shifting mystery. These phenomena push the boundaries of our understanding, challenging scientists to rethink the very nature of existence, locality, and causality, fundamental principles that, until quantum mechanics seem like the bedrock of scientific inquiry. Quantum mechanics might reshape our understanding of the universe by opening doors to realities beyond our current perception, creating new technologies, and inspiring fresh perspectives on existence, time, consciousness, and causality. Its insights challenge many of the foundational assumptions we hold about reality, suggesting that the universe is far stranger and perhaps more interconnected than we ever imagined. Thanks for watching this video, and see you next time.